Oscillations are very common in nature. Take for instance a spring or a pendulum. Mathematically, we represent oscillation with cosine or sine functions with a maximum amplitude, a frequency, and a phase. We call oscillation harmonic when there is only one frequency involved in the motion. If we have more than one frequency, we need to have more than one cosine function, and in this case the oscillation is anharmonic. An example of harmonic oscillation is given for a spring with a rigidity constant k. In this case, we know that the equation of motion obeys a differential equation like, and its solution is just a cosine function as written above. We also know that what makes a mass oscillate at the end of the spring is the potential energy, which is quadratic in x. So we expect that whenever we have a potential which is quadratic, we will have an oscillation which is harmonic. And the corresponding system is called a harmonic oscillator. And this is why we called this quadratic potential harmonic oscillator potentials. So this looks like a rather specific case. So why are harmonic oscillators so important in physics? Take the expression of a potential which is completely arbitrary but which has a minimum. Near the minimum, if we look only at small motion near the minimum, we will always recover a harmonic oscillator. To see that, we can write potential energy with a Taylor expansion around this minimum position. So if we only look at the first order, we have a term which is the first order derivative of the potential, but at the minimum this is 0 because this is a stationary point. So we need to go to the next order of the Taylor expansion. And in the second order, what we see is a second derivative of the potential, and this one is not 0, and it's proportional to the displacement squared. So we see that in this case this is a potential which is a harmonic oscillator potential. So if we only look at small oscillation, we can neglect higher order, which are cubic or quartic, etc., in the displacement, and we find an harmonic oscillator potential. So very often a system is found at rest in its minimum of energy. So a small perturbation, a small excitation of a system induce very often a harmonic oscillation, and this is why harmonic oscillators are so important in physics. So let's look at the case of a harmonic oscillator for a quantum system. For instance, this could be a molecule made of two atoms which can vibrate one with respect to each other. So the distance between the two atoms is what is expected to oscillate. We could also have for instance, vibrations of atomic nuclei. So atomic nuclei are made of protons and neutrons. They are extremely small. Their size is typically 10⁻14 meters. But nevertheless, we can study their shape and how they oscillate. So for instance, they can be elongated or squeezed, and that will be characterized by the coordinate of the harmonic oscillator. We can also have oscillation between other type of shapes like pear shapes, etc. So let's imagine we have an experimental system which is able to measure x as well as the energy. So that will give us some point in this diagram. To calculate the total amplitude of probability at this point, I will need to sum over all possible path, which is too complicated. So naturally, one way to simplify the problem is to use the semi-classical approximations in which we only keep the classical path. We know that classical path for the harmonic oscillator are expressed as a function of cosine function, as we saw earlier, and with a unique frequency. where we have introduced the angular frequency omega, which is just 2 pi times the usual frequency. Before we use the semi-classical approximation, we should compare the actual value of the action for the classical path and compare it with h bar. So I let you calculate the action for this classical path as an exercise, and what you should find is the action is actually equal to 0. So obviously the action cannot be considered as greater than h bar, and using classical path make no sense here. So we either need to solve the problem exactly starting from the Schrödinger equation, and that's not something we are going to do. You will eventually do that in next year if you take the quantum mechanics course.